Hello, everybody. I hope you've been studying hard since the last time we spoke. Today, I want to go on with the fourth part of our energy series and talk to you about fossil fuels. And what I'm going to do with fossil fuels in the next several videos is as follows. First, we're going to look at an overview of fossil fuels, and then we're going to look at coal, and we're going to look at all the issues that come along with coal. And we'll also look at some of the ways coal might be cleaned up. And then we'll do the same thing for oil and natural gas. And after that, we're going to look at what are the more modern fuels, the so-called synthetic fuels, and we'll put fracking in that for natural gas. And we'll look at the tar sands in Canada and a few things like that. So let's get started. Fossil fuels comprise coal, oil, and natural gas. And they are composed of remnants of prehistoric organisms that existed millions of years ago on Earth, actually hundreds of millions of years ago on Earth, much of it from about 300 to 350 million years ago. And for that reason, it's called fossil fuel, because what's left of those organisms, other than coal, oil, and natural gas, are fossils. And as we saw earlier, they supply over 80% of the energy used in North America. They are a non-renewable resource because they are created much too slowly to replace, especially at the rates at which we're using them. And they represent energy that was captured by life hundreds of millions of years ago. So in a sense, they're an energy bank account. They are unequally distributed around the globe, and in a second I'm going to look at some maps. You know I love to look at maps. I'm going to look at some maps to show you where these fuels are distributed. So here are coal deposits, and notice that the red deposits are the higher quality coal, and the green deposits are the lower quality coal. And you can see that the United States actually has a fair amount of coal, as does China. South America and Africa has very little coal, but Australia and Europe also has a large amount of coal. So that's the inequity of coal distribution in the world. Let's look at oil. So here are oil deposits, and you can see that the red designates the known major oil and gas reserves, and the yellow indicates places where we think there might be oil and gas in the future. And notice this huge area up north of Russia in the Arctic Ocean. And you may recall seeing in the film Rex Tillerson and Putin shaking hands over an agreement between Exxon and the Russians to develop those oil fields. And then extreme oil, these are these synthetic fuels, these really difficult to get out fuels that we'll talk a little bit more about. So how were fossil fuels formed? Well, coal and natural gas is methane or CH4. Hundreds of millions of years ago, the climate was very mild, and that meant that there were vast swamps in many of the land areas, and dead plant material, when it falls into a swampy environment, decays very slowly, because oxygen gets easily depleted in water, and decomposition requires oxygen to become complete. So what you get is you get an organic muck forming in these swamps, and as these mucks get buried by what's called in the middle panel here dirt, but really it should be called sediment, mainly mineral particles, you get a lot of pressure, and then you get heat, and it turns these dead plants into coal. And so coal is formed by the partial decomposition and then heat and pressure treatment of former land or swamp plants. And this is what we imagine the process to look like. When these plants first decompose, we call that substance peat, that poorly decomposed organic matter. But over time, with heat and pressure, they get turned into lignite, which is a low energy coal, and then into true coals, things like anthracite. And we'll talk more about the grades of coal in a little while. Now let's look at how oil is formed. Petroleum and natural gas, don't forget natural gas is methane, they are formed due to aquatic organisms that die and settle to the bottom and fail to decompose at the bottom of the ocean because of the lack of oxygen, and they get covered with sediment in the same way that the decaying material in swamps gets covered with sediment. And over time, heat and pressure turn them into hydrocarbons or into oil. And natural gas is formed the same way, but it's often at higher temperatures. So if the temperatures were higher, you get more gas and less oil formation. So let's turn our attention to coal. And this is what coal looks like. And I realize that many of you may not have seen coal in your life, whereas in my lifetime, when I was a kid, I would walk down the street and find it commonly scattered or littered on the street because coal deliveries were common to every apartment building as I walked from my house on 8th Street to PS 41 for elementary school. The issues with coal are that it currently has a fairly limited supply, and we'll talk more about that. The second issue is that it burns really dirty. There's lots of particulate matter, and by particulate matter I mean soot or dust particles that represent incompletely burned coal. In addition, acid is formed from the coal combustion, and that leads to acid deposition. And coal also causes other air pollutants, and we'll talk a little bit about them later. The mining practices of coal are also highly destructive, both to ecology and to the human beings who participate in them. And there are huge external costs, and we'll talk a little bit about that. So those are the big issues with coal. Let's look at them. Many experts believe that most, if not all, coal deposits have been already identified on the planet. The U.S. has about 25% of the world's coal supplies, and you can see that from this graph on the right. And so we're in good shape for coal. Known coal deposits are thought to be able to last us for about 200 years at the present rate of consumption. The most optimistic estimates suggest there might be as much as 1,000 years of coal left. So we're going to run out of coal at some point. The question is, should we use it all up and leave the planet with no coal? Should we use it all up despite its CO2 issues? Or since human beings have to change eventually away from this fuel, should we do that now? Should we not pass that problem on to a future generation? I'll let you figure out what you think about that. Now, coal comes in different grades, and this is important to know. Anthracite, you can see in this table down here, anthracite contains the most energy. It contains about 14,000 BTUs per pound, whereas lignite, less than half that amount. And you can see the price, the 2009 price at the mine for a ton of coal, $60 for the good stuff and $21.53 for the poor stuff. And I'm not sure why sub-bituminous coal is cheaper than the lignite, but my guess is that it has more pollutants and therefore they're looking to get people to buy it, and many people can't because of environmental regulation. The different grades are due to differences in heat and pressure during formation, as well as the length of time that the coal has been forming. So let's now take a look at coal mining. Coal is usually found in seams, that's what they call it, that vary from 1 inch to 100 feet in thickness. And there are two ways you can extract coal. One of them is surface mining. You simply dig a big pit, and that's what you can see in this picture at the right. This is usually what is done if coal is within 30 meters of the surface. It goes by many names. It's known as strip mining, open pit mining, and mountaintop removal. And we will look at mountaintop removal in a little bit. Then there's subsurface mining, and that's what you might think of as a mine, where you have a mine shaft and you see these railroad-like trolleys going down into it, and you see miners who are dirty with headlamps on and covered in coveralls underground extracting minerals. That's subsurface mining or shaft mining. Coal mining is an exceedingly dangerous occupation. During the 20th century in the United States, more than 90,000 coal miners died in coal mine accidents. So that's almost 1,000 miners a year dying in accidents. Miners have an increased risk of cancer, and there's a special disease of the lungs, specific to coal miners called black lung disease. And in the 20th century, approximately 2,000 miners died from these diseases each year. If we get a chance in class, I want to show you a video of Johnny Cash singing about the hazards of coal mining. Coal emissions are a big problem in terms of air pollution and also in terms of environmental disease. So we want to look at this for a second. Combustion of coal produces more carbon dioxide per ton than does oil or natural gas. So that's one way that it's dirtier, in that it just creates more carbon dioxide. Second, it produces huge quantities of particulates, which, as I said earlier, are partially burned residues that comprise soot. And soot not only increases the need for cleaning. A friend of mine once told me that at the turn of the 20th century, you could not buy white suits in Pittsburgh because of all the soot in the air from the coal burned there. But it also has a significant health impact in terms of lung disease and cancer risk. Coal also produces a tremendous amount of mercury emissions. About 33% of airborne mercury emissions come from coal. And as we will see in the health unit, mercury is a particularly damaging toxin, and it bioaccumulates, which means it tends to stay in organisms once it gets there. Coal produces large quantities of sulfur oxides and nitrogen oxides, and these cause acid deposition. We used to call this acid rain, but we discovered that the acidity comes down not only in rain, but also in dust. In some areas, rainwater has been recorded to have a pH as low as 2. Now, in terms of the environmental impacts of mining coal, strip mines clearly destroy ecosystems and leave behind a wasteland that is often toxic. Abandoned strip mines are a pile of mineral rubble, and as a result, primary succession, which we haven't learned about, but that means that you're starting with rock and you need to reform soil, which can take a tremendously long time. And so after strip mining, primary succession, soil reformation must occur. The slag, which is the stuff that used to be underground and is now just laid out in the open air, is now exposed to a very high rate of weathering, and it typically leaches toxic and acidic materials into the surrounding watershed, and that can either go into rivers and streams, or it can percolate into the soil and therefore go into groundwater. In addition, the slag increases the rate of erosion, so you also have that issue, silt getting into waterways and clogging them up. In 1977, the Surface Mining Control and Reclamation Act changed the ability of coal companies to leave behind an ecological wasteland. So this was a real victory for environmentalists. And it required reclamation of surface mines, but only those started after 1977. It required permitting and inspection of active coal mining sites. It prohibited coal mining in certain sensitive ecological areas. And land with mines abandoned prior to 77 are slowly being restored with taxes collected from companies currently mining. So you can imagine that the coal companies did not like this, and that this had a negative effect on the ability to mine coal. So far, as of about 2010, about $1.5 billion has been spent by the federal government restoring coal mines. Now, just to show you one of the most egregious ways that coal was mined in the past was in a process called mountaintop removal. And I think you're going to find this hard to believe that it actually occurred. The tops of the mountain are removed, and then the slag is simply thrown over the edge and allowed to sort of avalanche down the mountain towards the stream beds. And you may say, oh, who would have done this? But the estimate is that somewhere between 15 and 25% of all mountains in West Virginia have been destroyed by mountaintop removal. Since 2002, it has been severely curtailed. But think about it. It took until 2002 to stop this process. And you can see in the graphic the steps in mountaintop removal. And the other thing about mountaintop removal is that it changes the topography, like you see here, of the undulating mountains and valleys, and changes it to look something like this. So that is the problem with one of the worst ways in which coal mining has been done. There are ways to make coal cleaner once it is being burned, and those are through smokestack technologies. But the smokestack technologies are costly. Now, you might hear that these environmental technologies make things more expensive, or is a government burden on industry, or is decreasing competitiveness of coal. But the way I think about it is that this is just the cost that you need to pay for coal to cover the cost of the externalities produced by burning coal. Not by mining coal, just by burning coal. As we will see, there are some severe externalities just from mining it. And you could have guessed that already by the number of deaths and the amount of disease that occurs from mining coal. So, for example, we can get rid of the sulfur in the smoke from burning coal by using scrubbers. And the scrubbers basically desulfurize the smoke. Sulfur oxides, instead of being emitted into the air, are caught in the smokestack. And this eliminates the acid deposition hazard. They're very good at this. They remove close to 99% of the sulfur from the power plant's exhaust, but they're expensive. And they create huge amounts of sludge in the form of calcium sulfate that must be safely disposed of. The sludge problem can be reduced with what is called resource recovery. And that's using the sludge and the fly ash to do other things, such as condition soil or turning it into drywall or something like that. The problem with this is if you put it as a fertilizer onto soil, it would be pretty good at that if there weren't other contaminants, such as heavy metals, including mercury. Even with a scrubber, there is still an environmental hazard. There's also something called fluidized bed combustion, and this is another technology that reduces sulfur and nitrogen oxides. And basically what you do is during combustion, crushed limestone or some other solid is mixed with the coal, and the sulfates are removed into a sludge at the bottom, so you have the sludge problem. And this runs about 100 degrees cooler than a typical boiler, and this means that you have higher efficiency, which means less soot, and fewer nitrogen oxides produced, so that's good. And the cost can actually be lower than conventional boilers, but the problem is sometimes these things seem to have a diminished lifespan. But it's another technology that can be used, and we should see this as the price of using coal. So those two technologies are ways of dealing with the acid deposition, the sulfur oxides and the nitrogen oxides that come out of the smokestack. But now we still have to deal with the carbon dioxide that comes out of the stack. So one idea is this idea of carbon capture and storage, abbreviated here as CCS. And it's a brilliant idea. Capture the CO2 in the exhaust and turn it into a solid carbonate mineral. And that mineral then can be buried safely, or at least that's the theory. The problem is it's really expensive, although it's cheaper to do it beforehand than trying to retrofit plants later. And there's a schematic of how that might be done on the right. It's in the experimental stage, or should I say really the trial stage, but there's great debate as to whether it should be pursued. And we might in class look at the debate as to whether carbon capture and storage should be pursued or not. Lastly, I want to talk about the external costs of coal. There are some very impressive external costs of coal. And let me show you a few studies that have been done. A 2008 study in Europe estimated that the annual cost of coal combustion and coal mining in Europe was 357 billion euros. And they only examined costs due to climate change, human health costs, and mining fatalities. Here's another study. A 2010 Clean Air Task Force study found that in the US, particle pollution from burning coal caused an additional 13,200 premature deaths, 9,700 additional hospitalizations, and 20,000 additional heart attacks. A 2011 Harvard University study found that the annual costs to local residents in Appalachian counties where coal mining was prominent was approximately $75 billion in healthcare costs alone annually, and that the total external costs in these counties were as high as $500 billion. The authors estimated that the cost of energy from coal would have to increase 2 to 3 times to cover these external costs. These studies are conservative estimates in general because several kinds of damage are very difficult to estimate and therefore not included in the study. And I just want to say that if you're asking yourself right now, how do they make these estimates? Well, these are what people who get public health degrees are studying. And so you can look at schools of public health if this kind of study is interesting to you. And they look at ways to estimate damages to an entire population. So that is it for today. I hope after this talk you have a good understanding of coal, how much coal is left, and the issues surrounding coal. And as we have seen, there have been considerable issues for the people who mine coal, for the people who live around where coal is mined, for combustion of coal in terms of air pollution, and that air pollution causing issues, health issues in particular, and that there are technologies to deal with these, but they are expensive and they would increase the price of coal. So until next time, study hard.